Okay, so advanced chemistry, chapter 1 review. We're going to go over the guided notes, so have your guided notes out and be filling them in as we go through it. Okay, so it's been a while since you've had chemistry. We're going to talk a lot about, in this review chapter, the periodic table. We're going to talk a lot about stoichiometry and different calculations that we learned. Some of the more difficult concepts from last year. So let's get started. Let's start with the periodic table. So many scientists help contribute to our modern periodic table. This guy right here, Dmitri Mendeleev, is given the most credit. How come he's given the most credit? Well, let's go back to his background. He was a Russian chemist who correctly predicted the existence of properties of undiscovered elements. So he was creating the periodic table, but he left holes because he knew there would be an element discovered someday that would fit in that spot on the periodic table. And as it turned out, he correctly predicted the existence of all the elements. And so he's given the most credit with creating our modern periodic table. So a Russian chemist, Dmitri Mendeleev. Okay, the elements on the periodic table are arranged by their atomic number, which is the number of protons, right? So Ruben,
Yeah.
how many protons does oxygen have?
9 or 6.
Oxygen.
I'm blind.
Jared, help him out. 8. Oxygen is on the periodic table, its atomic number is 8. That means it has 8 protons. Okay? Nate, how many protons would sodium have? 11. Its atomic number is 11. So again, remember, the atomic number is the number of protons found in its nucleus. Okay, the modern periodic table contains boxes. And these boxes contain the elements' name, symbol, atomic number, and atomic mass. So if you look at our periodic table, it's got the name, the atomic number, the atomic mass, and it's got a symbol. The symbol is usually 1 or 2 letters that helps identify that element. On the periodic table, if you have a column, remember a column is a vertical column. The columns of the elements are called groups or families. Groups or families. We'll talk about why they're called groups or families here in a second. On the periodic table, if you have a row which is horizontal, they're called periods or series. Periods or series. Elements in groups number 1 and 2 and 13 through 18. So 1 and 2 and 13 through 18, if you look at your periodic table, those are elements that possess a wide variety of chemical and physical properties and are called the representative elements. So 1 and 2, these 2 columns, and 13 through 18, this whole chunk of elements, these are called the representative elements. Elements in groups 3 through 12, that chunk that we just left out, are known as the transition metals. Elements are classified as either being a metal, a nonmetal, or a metalloid. If you remember last year, another name we gave for metalloid is semi-metals. So if it's touching the staircase, we call them metalloids or semi-metals. Okay. So let's talk about the metals. The metals are below the staircase in the periodic table. If you look at the staircase, so if we're talking below the staircase, this is most of the elements of the periodic table. So let's talk about them. Metals are elements that are generally shiny when they're when smooth and clean. They're solid at room temperature, and they're good conductors of heat and electricity, which means they conduct electricity, and heat can travel through metals very easily. Okay, let's talk about the alkali metals. This is group 1. That's this first family right here on the periodic table, group 1. The alkali metals are all of the elements in group 1 except for hydrogen. Remember, hydrogen is over here only because it has 1 valence electron. But it's not a metal, it's a gas. We made it in lab last class period. It's definitely a gas. So it's not a metal. It's there because it has one valence electron. But the alkali metals are very reactive. These guys love to react. Why? Does anybody know why they like to react?
Because they need 7 more valence electrons.
They have one valence electron. How many do they want?
8.
8. So is it easier for them to get 7 more or get rid of one?
Get rid of it.
They're going to get rid of one. And so they're going to react with almost anybody to get rid of that one valence electron. So that's why they're very reactive. Okay, let's go to group 2. These guys are called the alkaline earth metals. That's the family name. The alkaline earth metals. And they're also very reactive, starting with beryllium all the way down this group here. 2 valence electrons. Easier for them to gain 6 more or lose 2? Lose 2. And so they're looking to lose those 2 valence electrons. They're very reactive as well. Okay, let's talk about this middle chunk of elements, groups 3 through 12. They're known as the transition elements. And they're divided into the transition metals and the inner transition metals. If you notice on the periodic table, there's, on the very bottom, there's 2 long rows that are kind of taken out of the periodic table. We call these guys the inner transition metals. They're called the inner transition metals because they really should fit inside the periodic table right here. But to save space, they have put them, they just kind of drag them down to the bottom and taken them out. So they're called the inner transition metals. Okay, the 2 sets of inner transition metals are called the lanthanide series. If you look there, this La is lanthium, so it's called the lanthanide series, and actinium is the one below it, AC, so it's called the actinide series. And they're located at the bottom of the periodic table. Okay, now let's go above the staircase. Let's go above the staircase on your periodic table and look at the nonmetals. So nonmetals are elements that are generally a gas, or brittle, dull-looking solids, or poor conductors of heat and electricity. Group 17, if you look at group 17, this has a family name. They're called the halogens. It's composed of highly reactive elements. Anyone want to guess why they're highly reactive? What do you think, Tanner? Yeah, they have 7 valence electrons. They want 8. So they're trying to pick up one from anyone they can get it from so that they can have 8 valence electrons and be stable, like a noble gas. Good job. Okay, group 18. Group 18 is the most famous family on the periodic table. They're called the noble gases. They are extremely unreactive. Anyone want to guess why they're unreactive? They already have 8. They don't want to give or take any electrons from anyone else. In fact, they won't react with anybody because they're already stable. And so when you find them in nature, they are just by themselves. They're pure. Okay, this is a slide that has the periodic table. Let's just go through it, guys. What is this family name called?
Alkali metals.
The alkali metals. What about group 2? Alkaline earth. What do we call this big chunk of elements right here? Transition metals. Good. There is a staircase here. You look, I'm trying to draw the staircase in. What does that staircase separate, guys?
Gases.
What's below the staircase?
Metals.
So all of these guys, they're called what?
Metals.
The metals. Good. What do we call everything above the staircase? The nonmetals. What if it's touching the staircase? The semimetals, or some people call them metalloids. Good. What do we call this family, group 17?
Halogens.
They're called the halogens. Good job. And finally, the last column. That's the noble gases. Good job. What did we call these 2 horizontal rows at the bottom? The inner transition metals. Why are they called inner transition metals? They really fit in the periodic table up here, but to save space, they pulled them out. Good. Very good. Here's just another periodic table. There's a lot of different ways to organize it and color it up. Let's talk about the groups and valence electrons. Group 1, how many valence does group 1 have? 1 valence electron. Group 2 has 2. That's easy to remember. Now we skip the transition metals. You skip the transition metals because they drop down to a different energy level. But you skip the transition metals, then we're to group 13. Group 13 has how many valence electrons? 3. So what you do is you take the group number and you minus 10 from that. So if you take the group number 13 minus 10, you get 3. Group 14 would have how many? 4. Group 15? 5. 16 has 6. 17? 7. And 18 has 8. Except for, which one in group 18 doesn't have 8? Helium has how many? 2. Okay, very good. And so this, if you remember from last year, is the electron dot structure. It has the element symbol. So for hydrogen, it's got its symbol H, and it's got 1 dot. The dot represents what? The valence electron. So everyone in group 1 has 1 dot. You'll notice that in group 18, helium has only 2 dots, but after helium, they all have how many? 8. And so they're very stable. Okay. Let me ask you this before we go to the next slide. Who do you think sodium is really going to like on the periodic table? Chlorine. Yeah. How come? How come these two really like each other? Isn't that a... Yeah, it's a natural fit, right? Sodium wants to have 8, so it's looking to get rid of its valence electron. It's looking to get rid of this guy right here. Chlorine has 7. It wants 1 more, so it takes it from sodium, and those two form what's called an ionic bond. We'll talk about that in a second. Okay. So here's a picture of the periodic table. I'm going to pass them out. Actually, Tanner is going to pass them out. Thank you. And we're going to go through and label everything that we know. Okay? So what I would like to see you guys do, above group 1, what are you going to write right here? 1 VE, the 1 valence electron. What charge will these guys form? That's something we haven't talked about. +1, very good. How come they form a +1 charge? They're giving away 1 valence electron. When you lose an electron, you become positive. And so that's why they're +1. Okay, let's go to group 2. What are you going to write above group 2? 2 VE. And what else? +2. Again, why is it +2? Because now these guys are giving away their 2 valence electrons. Very good. Okay, we're going to skip this chunk of elements, but what is it called? Transition metals. Good. So we're going to skip them. They drop down in energy levels. So let's go to group 13. What are you going to write here? How many valence?
3
VE. 3 valence. And what charge do they form?
+3.
Plus what?
3.
+3. Okay, let's go to the next column over. What are you going to write?
4 valence electrons.
4 VE. And what's their charge?
±4.
Yeah, for these guys, it's just as easy for them to lose the 4 electrons as the valence electrons as it is to gain 4. So it's a little bit unpredictable here. They can either be plus or minus 4. Let's go to this this next group. How many valence in the nitrogen group? 5 VE. What's their charge though?
-3.
Yeah, these guys, now it's easier for them to gain 3 more electrons. And so when they gain 3 electrons, they're going to get a -3 charge. Let's go to oxygen's group. How many valence?
6.
6 VE. And what's the charge?
-2.
-2. They got 6 valence, so they only need 2 more electrons. When they get those 2 electrons, they're going to have a -2 charge. Let's go to the next group. How many valence?
7.
7 VE. And what's the charge?
-1.
-1. Okay, very good. And finally, the noble gases. What are we going to write above it? How many valence? 8 VE. Except for helium, which has 2 VE. Maybe make a note of that. What's their charge going to be? 0. They don't have a charge because they're not going to gain or lose valence electrons. They're already stable. Okay. Make sure that we have this staircase kind of drawn in. Everything below the staircase is a metal. Everything above it is a nonmetal. let's maybe make this note at the bottom of your periodic table. Let's go let's go with bonding. We're going to talk about bonding in just a second, but since we're labeling this, what if it is a metal and non-metal? What kind of bond is that? That's called an ionic bond. Okay, that's good to remember. What if it is, let's go to two nonmetals? Okay, two things above the staircase would be covalent bond. Okay, and what if it's two metals? Yeah, good. That one's easy to remember. It's two metals. It forms a metallic bond. Okay, that's pretty good from first year chemistry. If you can remember all of that, you're doing pretty good. Okay, now let's talk about chemical bonds. A chemical bond is a force that holds a group of atoms together. So a chemical bond is a force that holds a group of atoms together. So can you have a chemical bond with just one element? No. It's got to be at least two elements or two atoms, and it's a force that holds them together. Okay. There's three types of chemical bonds. We just talked about them. The first one is an ionic bond. In an ionic bond, there is a complete transfer of electrons from one element to another. We kind of talked about it before. Sodium has one valence electron. Chlorine has 7. Sodium is looking to get rid of that electron because it doesn't want it, and chlorine is looking to gain it, and so it totally transfers that electron to chlorine. When that happens, you get sodium, which now has a +1 charge, and chlorine, which has a -1 charge. And opposite charges will attract each other. So there's the bond between this positive sodium and the negative chlorine. They now will stick to each other, and that's what an ionic bond really does. Why is it called ionic, guys? Because it's formed by ions. Yeah, sodium is a positive ion. What do we call a positive ion? A cation. And the chlorine is negative. It's called an anion. And so that's why it's called an ionic bond. It's a force of attraction between the positive cation and the negative anion. All right, let's go to number 2, covalent bonds. Covalent bonds occur between two nonmetals. So they're above the staircase. And what they do is they share their electrons. They share the electrons. An example of this would be hydrogen has one valence electron. If it was to bond with another hydrogen, again, they're looking for two valence electrons. It wants to be like helium. And so they'll come together and share. And each hydrogen atom here feels like it has two valence electrons, which is what makes it stable, and it wants that. And so chemists would write a covalent bond with a line between them. And so hydrogen is diatomic, and so that's why it's diatomic. Okay, they share the electrons between them. All right, number 3, metallic bonds. In a metallic bond, there is a sharing of electrons in what we call a sea of electrons. They don't really claim their electrons, they kind of just all share it between them. And that's what makes metals such good conductors of electricity, is that they're not really claiming those electrons. Those electrons are able to flow, and that's what we call electricity, is flow of electrons. So if it's talking about a sea of electrons, you know it's talking about metallic bonds. Any questions there? All right, chemical bonds occur between the transfer or sharing of valence electrons only. Valence means this outer shell of electrons. We're not talking about the inside electrons. Those are not involved in bonding. The only ones that are involved in a chemical bond are the valence or these outer these outer shell of electrons. For example, let's just look at one. So this slide says, even though the element Einsteinium, its atomic number is 99. So how many protons would it have? 99. How many electrons does it have? It has 99 electrons. But how many of them are available for bonding if it has 2 valence? Only 2. So this electron and this electron are the only 2 that are going to determine how it bonds with other elements. All of these inside electrons here, they don't do anything with bonding. Okay, let's talk about ionic compounds. Ionic compounds is composed of a metal and a nonmetal. So we talked about that earlier. So if it has a metal and a nonmetal atom in it, it's called an ionic bond. An example is sodium chloride. Why is sodium and chlorine atoms held together? We just kind of talked about it. The sodium loses that 1 valence, becomes positive. The chlorine will take sodium's valence electron and become negative. Well, this attraction between positive and negative charges, that's what holds an ionic bond together. Now let's review. This was maybe one of the more difficult concepts in first-year chemistry, naming ionic compounds. Chemical nomenclature. This is a systematic way of naming compounds. So chemists like to have a systematic way so that everyone does it the same. Let's go through the rules to naming them. Okay, number 1, you name the cation, which is the metal, first. And you just name it its regular name, followed by the anion. So you name the metal, then the anion. Number 2, for monoatomic cations, use the element name. So all that's saying is just name the metal, whatever it is. On the periodic table, look up its name, and that's its name. Number 3, for monoatomic anions, this is the nonmetal, use the root element name, but you change its suffix, which means the ending part of the word, to IDE. I think we'll remember this from last year. And number 4, to distinguish between different oxidation states, or charges, of the same element, the oxidation state is written in parentheses after the name of the cation. We'll get to that. It'll make more sense when we look at an example. And number 5, when the compound contains a polyatomic ion, you name the cation followed by the name of the polyatomic ion. You just look it up on the table and that's it. Okay, let's go through some examples. Lithium is a metal. So how would you name it? Just lithium. All of these are metals, so as you look at the metal name here, you're going to notice that the ion name doesn't change. Okay, but the nonmetal, that's where you got to pay attention with ionic bonding. The nonmetal name is fluorine, but how would you name it in an ionic compound? Fluoride. Remember, you got to change the suffix to IDE, and that's what they've done on all of these. Okay. Practice problem number 1. It wants you to name the following ionic compound. So we see Mg, which is magnesium. Is that a metal?
Yes, sir.
Yeah. So how do we write the name of Mg?
Magnesium.
Just magnesium. Just look it up on the periodic table and just keep its name the same. Now, Cl is what? Chlorine. How are we going to change its name so that we're following those rules? Chloride. Sodium. Remember, we got to change that suffix to IDE. So this would be called magnesium chloride. Practice problem number 2. Let's name this one. So Nick, what are you saying? Sodium. Na is sodium. And how would we change the name of oxygen? Oxide. Good. So sodium oxide. Practice problem number 3. Nate, Al, what is that? Aluminum. And then S is what? Good. Yeah, it's sulfur, but you're changing the name to sulfide. Good. Always got to add that IDE. Okay, so that compound there is called aluminum sulfide. Very good. Okay, practice problem number 4. Let's name this one. Eiley, what is Ca?
Calcium.
Calcium. So we're just going to write that name, calcium. And what's F? Fluorine. How do we change its name? Fluoride. Good. So that compound's name would be calcium fluoride. Okay, now let's get into this a little bit today, and then we'll stop after a few more slides. So going from the name to the formula is a little more complicated. So going from name to formula, let's do a few of those. When going from the name to the formula for an ionic compound, there are a few steps that will make it easy. Number 1, always write the charge of the ion above the name. That's what I always do. Write the charge of it above the name. This one's very important. Always do step 1. Step 2 is use the crisscross method. You'll remember that. I'll come back to you from last year. The crisscross method is where I'll show you. Number 3, if it can be reduced, if the numbers can be reduced, then you reduce it. What do I mean by that? Can 2 and 4 be reduced, guys?
Yeah.
Yeah, these two numbers can go into each other. 1 and 2 would be what it's reduced to. So, okay, let's try it. So this is giving us the name, and it wants us to write the formula. Potassium chloride. What's the charge of potassium? Potassium is K. It's in group 1, so it's a +1. Always write +1 above it. Chloride. What's the charge of chlorine? What is it?
-1.
-1. Okay, now that I've got the charges above it, now you do the crisscross method. You bring that one to here and this one to here. So if we're going to write the formula, potassium is K. What number goes here? Well, we never bring the signs. Okay, but the signs stay up there. We're just bringing the numbers down. Do I need to write a 1 in chemistry? No, it's implied. It's always implied in chemistry. So I'm going to keep that. It's just implied. Chlorine is Cl. What number do I write? Right here. Nothing, a 1. So potassium chloride would just be KCl. Okay, stick with me a couple more. We'll finish this up. Let's go. Cesium oxide. Cesium. What's the symbol? Sorry. Where do we start? The charges. Let's write the charge above it. What's the charge of cesium? +1. What's the charge of oxide? What is oxide? Oxygen. So it's a minus what? -2. Okay, now let's do the crisscross. Remember, don't bring the signs, just the numbers. All right, now cesium, what's its symbol? CS. What number do I write here?
2.
A 2. Okay. Oxygen is, our oxide is oxygen, so we write, what number do I write there? I don't. Can I reduce a 1 and a 2? A 2 and a 1? No, so that is the formula for cesium oxide. Okay, practice problem number 7. Strontium. What's the charge of strontium, guys?
+2.
+2. What's the charge of bromine? -1. We do the crisscross. Strontium is Sr. What number do I write here? Don't, because it would just be this 1, so I don't need to write it. Bromine is Br. What number do I write by the bromine?
2.
A 2. Can I reduce a 1 and a 2? No, so that's strontium bromide's formula. Okay, number 8. Let's do it for beryllium nitride. What's the charge of beryllium, guys? +2, if you look it up. What's the charge of nitrogen? -3, okay. So now what do we do? Crisscross it. Beryllium is Be. What number goes here? 3. Nitrogen is N. What number goes here? 2. Can I reduce a 3 and 2? No, so that's its final formula. Be3 and 2 is beryllium nitride. Okay, I think we'll stop there for now. And we'll continue on later.